Alright, welcome back to the pycse channel. I'm going to try something a little bit different today, that is to integrate Excel as a data source with Google Colab and Google Drive to do a nonlinear regression. So I'm going to take this paper on the vapor pressure of mercury as the example data, and let's scroll down to the main table. So basically this is a paper that tried to find a very accurate correlation for the vapor pressure of mercury as a function of temperature. So they have this big table over here on the right, and eventually they're fitting this equation to it. So they take the log of P over PC in this column and T over TC in this column. TC and PC are defined over here as constants. And these are the parameters that they end up getting with a fancy orthogonal distance regression. Today we're going to just try this with a regular old nonlinear regression. Alright, so the task is get all of this data, get this model with these parameters into Google Colab. This is too much data to type in by hand, and it's actually fairly tedious to get in Excel, but once it's there it's not too bad. And then we need to figure out somewhere in here what tau is, and I found it in here. It is 1 over T divided by TC. So we can take all of that information and get it into Google Colab. So let's go over to a Google Drive. So I'm logged in. This is my Google Drive, and I have an empty folder here. So let me just drag an Excel file in. And now here is our data, and we can open it here and see what it looks like real quick. We have that column of the temperatures. We're going to ignore this column. We have, this should be a column of the pressure in megapascals, and we'll ignore these other two columns as well. All right, so the first thing we should do is create our Colab. So we go to the plus menu and click on Google Colab, and let's go ahead and name it something other than this. Let's say mercury correlation.ipy notebook. All right, and then if we go back here, it should update that in a minute to have that name. Maybe I have to get off of there. And let's see if we refresh. We'll check back in a minute. And then since we're going to be doing some work here, I'll make some notes to myself from, let's just put a copy of this link in here so that you can find it later. And we'll just leave it at that. So the first thing we need to know about Google Colab is it's not like running on your desktop. Every time we start this, it starts up some virtual machine somewhere in the world, and if we look at what the current working directory is, we can see it with exclamation pwd, and this says that we're in /content, and if I try to say ls just to see what kind of files are here, what you see is sample data. What you don't see is anything that's listed here, like data XLS. And that's because we have to come over to over here and mount the Google Drive. So we're going to have to click on this, connect to Google Drive, and wait for it to do its job. Sometimes it will ask you to authenticate and copy a little key in, but that normally only happens with external things, like a notebook you drag in. And now if we look here, you can see we have this new thing that is my Google Drive, and it looks like I have two different pycse channels. I must have created one another day. But now we can find this file over here. All right, so let me show you how we get there. So after you go through that process and mount this, there's a couple of things we could do, but let's do import os and os.changedir, and the path to that is /drive/my_drive. Actually, you know what's easier is over here we'll just copy the path and then paste it. See, I already got it wrong. It's in /content/drive. And now I will put in the bang ls. And if we run that, you see that we have the data.xlsx and this Mercury correlation notebook that we named up here. All right, so that's the first step. Now we are in this directory and we can access the xlsx file. The next thing we need to do is get that contents of that data file into something we could use. So I like pandas for this, so let's import pandas as PD. And let's say df equals pd.readxl and then data.xlsx. And then we'll look at what happened when we do that. So that reads it in, and we now have a pandas data frame that you can think of more or less like a NumPy array if you want, but now it'll be easy for us to extract the TK and the P column. All right, so let's go ahead and do that. T equals df, and then we have to give it this name. T, we want the Kelvin. And let's do P is equal to df, and let's pick that one. Okay, and now we'll just look at these two, and you'll see that these are now they're the two things that basically act and for all practical purposes like arrays, but they're probably actually a series. Let's see. Yeah, so these are a pandas series, but they are for all practical purposes, they're going to be treated like arrays. All right, so there's that. Let's go back over here and look at these two parameters. We need to save TC and PC. Those are constants that we're going to use. So let's add that. TC is equal to 1764, and PC is equal to 167. All right, and we should probably put some units on those just to remind ourselves. Those are critical temperatures and critical pressures. All right, so then we need to define the Y data. So going back to the model, our model is log of P over PC. We're going to call this Y, and we're going to use T as our X variable. So let's go ahead and set up a Y variable here. Y is equal to np.log P divided by PC. And I probably need to import NumPy at this point. Import NumPy as np. All right, so there we have some Y data that we're going to look at, and we have T data that we'll use in our model. So for the next step, I'm going to just use the nlinfit function from pycse. That is a package that I wrote for this purpose. And since we're on Google Colab, we have to install it. So I'm going to just run that. And this is going to download and install NumPy or pycse, and it will have the nlinfit function that I want. All right, from pycse, import nlinfit. And since you might not be familiar with nlinfit, it's very similar to the one in MATLAB. It takes a model that we have to write, some X data, some Y data, some initial guess of parameters, and then a confidence interval. So 1 minus this number is the confidence interval. So this will give us the 95% estimate of the parameters. All right, so let's build our model. The model should look like, let's see if we can just copy and paste this. Model should look like this, and so we have to write def model the model is going to take t as the first argument, and then down here, if you notice, the model takes sequential parameters. So we're going to just say star pars here so that we can unpack a list into it. And the model is going to end up looking like this. We'll write out A1. I like to unpack variables so I can write them the way they look up here, is equal to pars. And we will want to return tc divided by t times a1 times tau. All right, let's go back up and say what tau is. T divided by tc. And then we need to put this in parentheses so it looks like this one, plus a2 times tau raised to the 1.89. You can see they just found something that is like moderately close to a power series with hopefully well-chosen values for the polynomials. Tau to the 8th plus a5 times tau to the 8.5 plus a6 times tau to the 9th. All right, is that a1 times tau, a2 times tau to the 1.89, tau squared, tau to the 8th, tau to the 8.5, tau to the 9th. All right, that's our model definition. And we need a guess. So again, we could come back up here. Let's, I'll copy this. And this is just pasting base 64 encoded image in here. It's kind of long, so I won't bother to look at it. All right, so here are the guesses. So let's just say we'll get kind of close, minus 4.5, minus 1.4, 2.4, minus 31, 58, and minus 27. All right, so that will be our guess, and they're just things that are kind of close to this. We're not expecting to be exactly the same because we're using a slightly different method for the fitting. All right, then we just say pars confidence interval standard error is equal to nlen fit. So those are the outputs. We provide our model function and the x values, the y value that we calculated above, and the guess. All right, and then let's look at the pars right away. So this should have printed those pars. Oh, everything is buried inside the function. So it wasn't doing anything. Now we get the pars. There's a little bit of a warning about the covariance could not be estimated, but we have minus 4.56, minus 1.45, 2.39, minus 30.5, 56, and minus 27. So those all look promising. And then let's see if CI might be undefined if they couldn't do that. So something happened where it wasn't able to estimate the covariance, so it's not able to estimate confidence intervals in this case, which is pretty strange since I just ran this in another system and it seemed to work perfectly fine. I don't know what to make of that. Let's see, did I make it maybe a different guess? 0.3. I don't think that should make any difference. Oh, wow, look at that, but it did. Okay, so a slightly different guess leads to a slightly different answer where you can get confidence intervals in here. So some things I like to see are no crossings of zeros, right? So both negative, both positive, both negative, both positive, both negative, and it looks like for the most part some of these bracket some of these, but in any event they're all quite close. All right, so I always like to plot my fits. So let's go ahead and do that. I actually usually plot things from the beginning, say t comma p. This would be the data that we were trying to fit on here. And a subtle point here is our model doesn't actually predict p, it predicts the log of p over pc. So if we want to plot that, we need to convert it, and so we'll say np.exp of model t, and then pass the pars in, and then here we have to say pc times that. And so let's make these ones blue dots, and let's make this one a red line. All right, and there you see the blue dots, and the red line looks like a good fit, and as far as we can tell, we have a good fit, and so that's pretty much the best you could hope for. All right, so that's the end summary today. The main point of the exercise was learning how to mount your Google Drive. You do that from this little button over here, and click on this, and if it is a new notebook that you've made in Google Colab, then probably it will just mount. Every once in a while you may be asked to authenticate in another browser window, and you'll get a little token that you have to copy and paste to do the mount. Then you have to change the directory into the place where you want to work, and that will give you access to the files that are in your Google Drive. And then from there out, it's like working on a local machine. Here I use pandas to read an Excel file, get the data, extract out the 2 columns into a series, write some parameters that we use for critical constants in the equation. We installed pycse to get nlen fit. That's just a wrapper around a least squares model that is in SciPy or NumPy. And then we use that to fit the data to this equation from that paper. And there was an initial guess in the paper. If there wasn't, you would have to come up with one by yourself, by some method. And finally, that we have the parameters that we estimated, and here is the fit that we could use. All right, that's it for today. Have a good weekend, and I'll see you next time.